Hello students, have you ever plucked a guitar string and let it vibrate freely? Or pushed a swing once and watched it sway back and forth? That's exactly what we call natural or free vibrations. When a body is disturbed slightly from its rest position and left on its own, it starts vibrating freely without any external force keeping it going. These vibrations are special because they happen at the body's own natural frequency. So yes, your guitar string, your swing, even a tuning fork, they're all showing natural vibrations in action. Now let's talk numbers. The time taken for one complete vibration is called the natural period, denoted by T. The number of vibrations in 1 second is called the natural frequency, denoted by F. And here's the key relation, F equals 1 divided by T. This means if the time period is short, the frequency is high, and vice versa. That's why small tuning forks produce high-pitched sounds, while larger ones give low notes. The math is simple, but the physics is powerful. So what decides this natural frequency? It depends mainly on the shape and size of the body. A long pendulum swings slowly because it has a larger period, while a shorter one swings faster. The structure and elasticity of the material also play a role. This is why musical instruments of different sizes sound different, even if they're made of the same material. Physics is basically telling us size and shape matter when it comes to vibrations. Let's now focus on amplitude, the maximum displacement. Ideally, in a perfect world, the amplitude of natural vibrations remains constant. That means if you pluck a guitar string in vacuum, it would keep vibrating forever at the same loudness. But in real life, air, water, or any surrounding medium resists motion, and gradually the amplitude decreases. This reduction is called damping. It's the reason why your swing eventually slows down and why your guitar note fades away instead of playing forever. So where can we find pure, perfect natural vibrations? The answer is in a vacuum. Since no medium is present to offer resistance, there is no energy loss, and the amplitude stays constant. But in air, water, or any real medium, vibrations lose energy over time, so amplitude reduces. In short, true natural vibrations are more of a theoretical ideal, fun to imagine, but impossible to achieve perfectly on Earth. Let's solve a quick example. Suppose we have a pendulum of length 1 meter and gravity is 9.8 meters per second squared. The time period t is given by 2 pi times the square root of length divided by gravity. Substituting the values, t equals to pi times the square root of 1 divided by 9.8, which is about 2 seconds. The natural frequency f is 1 divided by t, giving 0.5 Hz. That means the pendulum completes one swing back and forth every 2 seconds. Longer pendulums swing more slowly, while shorter ones swing faster. That's why wall clocks and pendulum clocks are carefully designed with exact lengths. Let's wrap it all up. Natural vibrations are free oscillations that happen when a body vibrates on its own after disturbance. The natural period t and frequency f are related by the formula f equals 1 divided by t. The frequency depends on shape, size, and structure of the body. Amplitude remains constant only in vacuum. In real conditions, damping causes it to decrease. And finally, a pendulum is a perfect example to understand how natural vibrations depend on length. So the next time you hear a guitar string fade or see a swing slow down, remember, you're watching natural vibrations and damping at work. Isn't physics beautifully musical?